Hello class, today we're going to talk about polynomials. And so here's what to look for when we're talking about polynomials, what they are. We're going to go over some examples. Let's put it into words first. So polynomials are the expressions whose variables have only non-negative integers as exponents. So non-negative being 0, 1, 2, 3, 4, so forth and so on. This means no radicals. No radicals would be fractional exponents. No variables in the denominator. Variables in the denominator could always be written as negative exponents. No logarithms, no trigonometric expressions, no exponential expressions, no variables in the exponent itself. Two more things to note. X to the power of 0 will equal 1. This means that any constant can also be considered a polynomial. The coefficients of a polynomial can also be any real number. Some definitions. The degree of a polynomial is the highest exponent with a non-zero coefficient. Okay. The lead coefficient is the coefficient of the variable with the highest exponent. So we look for degree and lead coefficient at the same time. And the constant is the term with no variable. All right, example 1. Determine if the expression is a polynomial. If it is a polynomial, determine its degree, lead coefficient, and constant. If not, explain why. So we have to look at the variables here. So I've got 3 here. This is 1. And this has no variable, but that's okay. So this is a polynomial. Okay. We're good here. So what's our degree? It says if it's a degree, determine its degree. The degree, as said on the previous page, is the highest exponent, and it's 3. So our degree is 3. Our constant, I think I skipped one, but we'll go with constant for now, is the number without a variable. So that's negative 1/2. And then I missed lead coefficient. Lead coefficient. We found 3 as the degree earlier. The lead coefficient is the 4 that accompanies it. All right, for the next one. This is not a polynomial. Why not? Remember, we want whole number or non-negative integers only. We have the negative 4. Negative 4 is negative, not a whole number. All right, for the next one, also not a polynomial. We have a radical involved. We can't have radicals involved when we're talking polynomials. So not a polynomial. We have a square root. Can't have a square root. Doesn't matter what's happening underneath the square root. Can't have a square root. And then finally, we will look at this last one, and this is a polynomial. So we're good here. Notice we would have a 1 exponent and a 4 exponent, so we're good. Polynomial, so the degree is the highest exponent, that's 4. The lead coefficient is the term that accompanies it, that'd be the negative 2. And then the constant is the term without a variable. Well, we don't have a term without a variable, so we, in that case, say it's 0. Now, real quickly on this one, because your homework may ask you this, this is not what's written in what's called standard form. We've seen standard form of a quadratic, but there are standard forms of a polynomial, and that just means you're writing the terms in, so the exponents are in descending order. We had it here. We had 3, 1, and then 0. Here we have 4 and then 1. Make sure if it asks you, this is how you were to write it in standard form. So go ahead, take the time to do the we do and then the you do, and then we'll talk about the answers. All right, first one. Is this a polynomial? And yes, it is. This is a polynomial. Now, we have to be careful with how we identify the degree. Because we have this binomial here, we'd have to expand it. I won't expand it. I'll just expand it. I won't actually FOIL it out. We'd have to do this, and we'd have to do all the distribution we want to find what its degree is. But luckily for us, that's easy if all we're looking for is the degree. You take this number, the highest exponent, and multiply it by here. So 2 times 3 is 6. The lead coefficient, take your 4, take it to the third power. 4 to the third power, that is 64. And then we would have the constant, same idea. Take the negative 5 and take it to the third power, which is negative 125. So just be careful with those. And then here, this is not a polynomial. We have a fraction exponent. All right. So for the next one, not a polynomial. Not a polynomial because the variable is in the denominator. And then finally, drum roll please, this final one is a polynomial. This goes back to one of the first slides I gave you where I said constants can be polynomial. It's trivial because we'd have to think of it as 7x to the 0, so that when we answer what's its degree, we'd say its degree 0. Its lead coefficient, well, it's 7. Its constant, also 7. All right, here we're going to talk about end behaviors. And what you see are a bunch of graphs, but they all have something alike. Notice they all have arrows in this lower region. They're all pointing down and to the left, okay? Whereas these ones up here are pointing up and to the right. These are odd degree graphs. You know, they would all have different degrees if we saw their polynomial, but all their similarities would be that they're odd degrees. And then they are also, their lead coefficient is greater than 0. Okay, so when we talk about end behavior, we're talking about really just a fancy way of describing what these arrows are doing. So these arrows down here, they are down and to the left. That means that when x approaches negative infinity, y is approaching negative infinity. Whereas these ones up here, as x goes to the left, that means when x approaches infinity, they're going up, which means y is also going to infinity. This is going to kind of become like a template for which you'll work. Now, these ones right here, these are even degree and a lead coefficient greater than 0. So now look at these arrows right here are all up and to the left. These arrows are up and to the right. So as x approaches negative infinity, again, that would be going to the left. Y, since they're going up, would go to infinity. And then for x approaches infinity, y approaches infinity, because again, they're going up. So again, a super fancy way of saying as x goes to the left, y goes up. As x goes to the right, y goes up. As x goes to the right, y goes up. As x goes to the left, y goes down. So let's look at it when we flip it. So here we would have odd degree. Notice everything's flipped now. This is up and to the left, and these are down and to the right. Well, the degree is the same, so odd degree, lead coefficient less than 0. Well, this would flip the narrative as x approaches negative infinity. Again, as x goes to the left, y is going up, so it goes to positive infinity. And so likewise, as x approaches infinity to the right, y is going down or approaching negative infinity. Finally, you might have guessed this is even degree. Okay. Lead coefficient, you guessed it, less than 0. And now everything is down and to the right. So as x approaches negative infinity, y is also approaching negative infinity, which means it's going down. As x approaches positive infinity to the right, y is also still going down, negative infinity. So a lot of terminology there, a lot of new symbols, a lot of ideas to get used to. Let's go over an example. Using the lead coefficient and the degree of the polynomial, determine the end behavior of the graph. Okay, so we've got a polynomial written in standard form. Its degree, we'll just write that out real quickly, is 6. That's right here. So that's even. And its lead coefficient is right here. That's 2. That's greater than 0. So we have an even degree with the lead coefficient greater than 0. Let's go back and check our charts. Okay. I got even degree, but this is lead coefficient less than 0. So I've got that right here. So the end behavior is this right here. We're just going to copy this down. So we're going to say as x approaches negative infinity, y approaches infinity. As x approaches infinity, y approaches infinity. Why is this important? Well, it gives us a distinct mindset into what the graph would look like. If we were to draw this out, it would give us a detail that these two pieces of information tell us that as x goes to negative infinity, that'd be to the left, y is going to infinity. So that means we're going up and to the right. Whereas x goes to infinity, or sorry, up and to the left. As x goes to infinity to the right, we're also again going up. So the end behavior would look like something like this. We don't know what the middle is, and over the course of the unit, we're going to learn to fill these details in, but we know this to be true. So go ahead and give this one a shot. Again, use the lead coefficient and degree of the polynomial to determine its end behavior. All right, let's go ahead and look at the degree. Again, the degree is 3. That's right here, so that's odd. And then the lead coefficient is -5. That's right here. So that's less than 0. So we're looking for odd and less than 0. So here's odd and less than 0. So here's our answer right here. Basically, as x goes to negative infinity, y is going to positive infinity. X goes to infinity, y is going to negative infinity. So let's write that down as x approaches negative infinity, y approaches positive infinity. As x approaches positive infinity, y goes to negative infinity. Let's again get kind of a visualization of what that would look like. So x goes to a negative infinity, that'd be left. Y is going to positive infinity, that's going up. As x goes to the right, positive infinity, y goes to negative infinity, which is down. So that's down like this. Again, we know the ends will look something like this. Again, we can fill in the details later, but that's what that would look like. All right, So we're given this information here for our last examples. Okay. We're going to try and sketch a rough estimate of what this graph would look like. Okay. So let's start with positive and negative intervals, because we know that positive intervals would be a graph above the x-axis, negative would be below the x-axis. That means these boundaries, as we've seen before, always mark the ends of those, which would be where it's 0. So let's focus on the boundaries, which would be -4, -1, 4. I've got another -4 here, another -1 here, 4. So our boundaries are -4, -1, and 4. These are our x intercepts. So that means these are the values that we're going to be plotting on the x-axis. So 1, 2, 3, 4. Okay. -1 and 1, 2, 3, 4. All right. So we know that it's positive after -4, and then, or from -infinity to -4. So let's go on to increasing and decreasing. So it's decreasing from -infinity to -2.67. Okay. And it's decreasing from 2 to infinity. So here from 2 to infinity. Now, the thing we have to accept with increasing and decreasing is we just know the x values. I'll write that out. Just know the x values, which means we're going to be taking some wild assumptions as to what the y values are. We're not going to know for sure. Okay, so -infinity is both decreasing and above the x-axis. So that means we got something that looks a little bit like this. We're above and it's decreasing till we get to -2.67. Okay. We get to -4 and then say -2.67 right there. Again, we don't know the y value, so we're guessing. Is this okay? Well, it's negative from -4 to -1. So this little interval right here. And then from -2.67 to 2, it's increasing. We'll go with a curve. We'll go right there. That's where 2 is. And then we curve downward. And from 2 to infinity, we're decreasing. And from 4 to infinity, we are negative. Let's try that part again. I don't have an undo button, so I guess I'll leave it. But the important thing to remember is this interval right here and this interval right here provide us with our starting and stopping point. Okay. So go ahead and give this a shot. Do the best you can, and then we'll go over the answer. All right. So let's start. We're always going to start by identifying our x-intercept. So we got -2, we got -2, we got -1, -1, 1, 1, 2, 2. So our x-intercepts are -2, -1, 1, and 2. Even if you're confused about all this right now, you should be able to do this. Okay? So -infinity to -2 is negative. So we're down here, and I'm guessing we are decreasing, yeah, or increasing. So we have an end behavior that looks like that. Okay. And then we go to about -1.5. I'll go right there. We'll keep it relatively close. From -1.5, we're increasing, and then we decrease. Well, we decrease from -1.5 to 0. And then we have to change directions again until 1.5. and then we decrease the rest of the way. So let's actually go over that a little bit differently, because I'm not loving the way I'm explaining that right now. We're going to keep our x-intercepts. We should always start there. Okay. Let's plot all these points first. We got -2. I'm going to choose a different color. That's a terrible color to use. -2, -1, 1, and 2. Now we're going to note these other values, -1.5. -1.5 is where we start increasing and then we decrease. So that means this is a maximum. Okay. Now, where does that fall in my positive negative intervals? -1.5 falls between -2 and -1 right here. So we're going to put that above the x-axis, like right about there. Okay. Now what about 0? 0 goes from decreasing to increasing. So something like that. Okay. So 0 might be right here. And then 0 falls between -1 and 1, which is in the negative interval. So yeah, that'll be below the x-axis. And then 1.5. 1.5 falls between 1 and 2, so it's positive. And it's going to be up, then down. Okay, so we can kind of connect our points from there. That's a lot better looking. We're done. Go ahead, give your exit ticket a try on paper, and go ahead and turn it in when you're done.